Hello guys, welcome back to Star X Education and Chemistry Exams Prep. This is Dr. Kulbhushan. In this question, we need to figure out the rate of reactions of the following 4 alcohols. So these reactions are actually dehydration of alcohols in presence of a mineral acid. Here it is phosphoric acid, and the reaction conditions are to heat the reactants as needed. So to answer this question, first of all, we need to see the nature of the reactants and the reagents and figure out what kind of reactions are possible. So let's name the starting alcohols first, and then we will see their nature. So to name alcohols according to IUPAC rules, you choose the longest carbon chain containing the OH functional group, alcohol functional group. So this is meth, eth, prop, bute. So this is 1-butanol or butane 1-ol. This is a primary alcohol. Primary alcohols are the alcohols that have the OH group connected to a primary carbon. And a primary carbon is a carbon that is attached to no other carbon or one carbon or carbon chain. To name compound B, we need to choose the longest carbon chain and then count our carbons. So we have meth, eth, prop, bute. So we again have a 4 carbon long chain, but this time the OH is connected with carbon number 2. So this is 2-butanol or butane 2-ol. This is a secondary alcohol, and the reason is because the OH is now connected with a secondary carbon, which is a carbon which is connected with 2 other carbons or carbon chains. Now the C is again a primary alcohol. So we start the carbons from where the OH group is attached. So meth, eth, prop. So now the carbon chain is 3 carbon long. So this is 2-methyl, 2-methyl propane 1-ol or 2-methyl propanol. Now compound D is a tertiary alcohol because the carbon that OH is connected with is a tertiary carbon. A tertiary carbon is a carbon that is connected with 3 carbons or 3 carbon chains. So to name this, we choose the longest carbon chain possible here. So meth, eth, prop. So this is 2-methyl propane 2-ol. And this is also known as tertiary butyl alcohol. That's its common name. The common name of these other 3 compounds are butyl alcohol, or N-butyl alcohol. The common name of 2-butanol is secondary butyl alcohol, and for the alcohol C, its common name is isobutyl alcohol. So these are very important points to remember because these methyl groups are very common and you will see them over and over in organic chemistry. So now we have named the alcohols. Now we need to see the nature of alcohol. So our alcohol functional group is ROH, which is ethanol, for example, CH3 CH2OH. So now we know that the oxygen has two lone pairs of electrons. Alcohols are also mildly acidic. So this bond may break in a reaction to give us acid-base reactions. The other bond that may break in the reaction is the OH. So the alcohols can also give substitution reaction. And the third type of reactions are the dehydration of alcohols, where the H2O leaves and you form alkenes. So in these cases we have phosphoric acid as a reagent. So apparently there would not be an acid-base reaction. So the possibility is the substitution reaction or the elimination reaction. And because for substitution reaction there must be a very good nucleophile present, which in this case of H3PO4 is not available. Therefore the reaction would be the dehydration reaction. And to do the dehydration reaction, we know that the H2O must leave from the alcohol to form an alkene, but the OH is actually a very poor leaving group. Therefore, first the OH gets protonated by the mineral acid phosphoric acid, and then carbocation forms as H2O is a good leaving group. So basically this question becomes the rate of elimination reactions of first order and the stability of carbocations. So the compound A, this forms a primary carbocation, and so the product would be this alkene, butene or 1-butene. So for this we need to see the stability of carbocation, which is a primary carbocation. Now compound B would give an alkene which is a bit more substituted than alkene A, and this is the result of a carbocation which is secondary in nature. So we have a primary carbocation in case of A, we have a secondary carbocation in case of B. In case of C, first we form the carbocation that is primary, but then we know that the primary carbocations can rearrange by hydride shift to give a higher carbocation, means a secondary or tertiary carbocation possible. So in this case, after hydride shift, we get a tertiary carbocation. So the product in case of C will also be the same as the product in case of D. So the product here will be this alkene, which is more substituted than in case of the product of A and B. Now to see the product of D, we form a tertiary carbocation here. So the carbocation is tertiary and the product is same as in case of alcohol in C. So this is in case of C, a tertiary carbocation, and in case of D, a tertiary carbocation. So now we have three types of carbocations. The first go through a primary carbocation, the second reaction goes through a secondary carbocation, and the third reaction and fourth reactions would undergo through a tertiary carbocations. We know that the tertiary carbocations are more stable than secondary carbocations, and secondary carbocations are more stable than primary carbocations. And these stabilities can be explained by inductive effect. So the stability of these reactive species is one of the applications of inductive effect that is used to explain the reactivity and stability of these organic species. So as we saw earlier, there are two types of inductive effects. So one is the positive I effect, where the electrons are given by a group or atoms to a center where there is an electron deficient atom. And the second one is minus inductive effect, where the electrons are taken by a group or atom from a place where there is extra electron density. And these electrons movement is through the sigma bonds. This inductive effect is the result of the difference in electronegativity between different connecting atoms. Those are connected by covalent bonds or sigma bonds. The inductive effect is actually a chain effect. It's a permanent effect and it's a compounding effect. Means if you have more electron donating groups, then the species would be more stable. So the case of carbocation is the case of a positive inductive effect, where electrons are given by methyl groups to the carbon that has a positive charge. The other applications of inductive effect are the polarity of a molecule, its solubility, acidity and basicity, and reactivity and stability of organic compounds and species. So if you want to quickly have a look why tertiary carbocation is more stable, you can see its structure. So the carbon that has a positive charge is sp2 hybridized. It's a planar species, and the sp2 hybridized carbon is more electronegative than these sp3 hybridized carbons. Therefore, the carbon that bears the positive charge gets electron density from these S3sp3 groups by inductive effect through sigma bonds. Now, if we see the secondary carbocation here, so the secondary carbocation has actually two carbon chains, and therefore the stabilization by inductive effect is less in case of a secondary carbocation. And if we have a look on primary carbocation, it has only one carbon chain that stabilizes the carbocation. And that's the reason that our tertiary carbocations are more stable than the secondary, and secondary carbocations are more stable than the primary carbocations. So these reactivities can be explained on the basis of inductive effect. So basically the question became the rate of elimination reactions, and that would be determined by stability of carbocations based on the phenomenon of inductive effect. So now let's have a look on our choices here. So now we saw that the tertiary carbocations being most stable here would give the fastest reaction, because if the reactive species are more stable, the reaction is faster. So we know that the primary carbocations are the least stable here. So the reaction would be fastest in case of a tertiary carbocation, which is compound D, and the slowest rate would be in case of compound A. Therefore, we can quickly eliminate some choices, like choice A, where it shows that A has higher rate of reaction than B, which is incorrect. So we can right away remove this possibility. Same way we can remove the choice B, because again A cannot be more reactive than D. Now C has D as option, which is the most reactive here, which is correct, but then it got the A, and A is the least reactive one. Therefore, we eliminate choice C, and we are left with choice D, where it shows that the D has higher rate of reaction than B, and B has higher rate of reaction than C and A, which is the correct option. Alright, so to recap this lesson through this question number 124, we saw the reactivity of alcohols. They give three types of reactions: acid-base reactions, substitution reactions, and elimination reactions. Dehydration of alcohols are a very common reactions of alcohols. And so these reactions take place in presence of mineral acids, because there are poor nucleophiles in the solution, and heating is needed, as primary alcohols wouldn't react in the cold solution. So very high heating is needed. Secondary alcohol will react when you warm up the solution, and tertiary alcohols would react right away. They may give you the product even without heating. So these are the properties of alcohols, and we also saw the rate effects due to stability of the carbocation reactive intermediates generated in the different reactions given here. And the stability of carbocations is tertiary carbocations are more stable than secondary, and secondary carbocations are more stable than primary carbocations due to inductive effect.